Well, it's Daniel here again, and welcome to another one of my video lessons. In my last lesson, we went through what redox chemistry is. We talked about what a redox reaction is, why they're important, what does redox mean, what is reduction, what is oxidation, what are oxidation numbers, oxidation states, in other words, and a little bit about how you would apply the rules for oxidation numbers and oxidation states. So if you haven't seen that video, I recommend you watch that one before you watch this one, because this really does build on the previous one. So last time we looked at the fact that group 1 metals would have an oxidation number of +1, indicating that when they bond they lose 1 electron. We looked at the fact that the chloride ion has an oxidation number of -1 because as a result of bonding it has gained 1 electron. And we looked at water, where the hydrogen atoms in water have partially lost an electron to the oxygen, because the oxygen is more electronegative, so there's not an equal sharing of the electrons between hydrogen and oxygen. The electrons in that bond are closer to the oxygen atom, and as a consequence, hydrogen's partially lost its outer shell electron, oxidation number +1, and the oxygen has partially gained 2 more electrons, so oxidation number -2. Okay, so where do we go next? Well, the next thing to look at would be looking at some of the rules for oxidation numbers. The rules come out from the definition that we went through. Oxidation number is a number of electrons lost or partially gained as a result of bonding. So there's a number of rules that sort of follow, things that generally happen or are always true, and they come from the definition. So if you really understand the definition and you apply it into a particular example, the rules sort of happen anyway. So let's look at a first example. Now, first example, generally speaking, let's look at hydrogen, for example. When it bonds, it would, generally speaking, partially lose an electron. Why? Because generally when hydrogen's bonding, it's bonding to something that is more electronegative than it. For example, carbon is more electronegative than hydrogen, so is oxygen, so is fluorine, so is nitrogen, and so on. So the general case would be hydrogen has an oxidation number of +1. There are exceptions. For example, in metal hydrides, group 1 metal bonding to hydrogen, for example, lithium hydride LiH, lithium, being a group 1 metal, will always lose an electron. In fact, group 1 will always have an oxidation number of +1, and it gives that electron to hydrogen in an ionic bond. So hydrogen's oxidation number in this case is -1, but these cases are quite unusual. So generally, as a rule of thumb, unless there's something odd going on or unusual going on, hydrogen's going to have an oxidation number of +1. But what about hydrogen, the element? Hydrogen gas, H2. Well, in this case, hydrogen is bonded to itself. There are 2 electrons in the shared covalent bond. They are sharing them equally. So the electrons, in a sense, what we're doing there is we're dividing those 2 electrons equally between the 2 hydrogens. So the hydrogens haven't really gained or lost any electrons overall. They now have a half share. Each hydrogen atom has a half share of 2 electrons, half of 2 being 1, which is exactly the same as the number of electrons it has in its outer shell. So where are we at? Well, hydrogen started before bonding with 1 electron in its outer shell. It still has 1, so its oxidation number is 0. So in hydrogen, the element, its oxidation number is 0. Hydrogen in covalent compounds, its oxidation number is +1. Hydrogen in the occasional ionic compound, when it's bonding with a group 1 metal, would have an oxidation number of -1. So what about other elements? Well, all elements, the situation is exactly the same as for hydrogen, because the oxidation numbers are going to be 0. So take fluorine, F2. The fluorines have equal electronegativity. They share the electrons in the bond equally. Therefore, its oxidation number doesn't change, 0. You can apply that rule to any element. So another one of the rules that you will learn about oxidation numbers is that the oxidation number of an element is always 0. What about simple ions? Well, that comes out of what we've already talked about with ionic bonding. So a simple ion, like a sodium ion, sodium loses an electron, it will have an oxidation number, therefore, of +1, and it will have a 1+ charge on the ion. So for simple ions, like sodium, and group 2 metal ions like calcium, calcium 2+, oxidation number +2, group 7 simple ions like fluoride, chloride, bromide, iodide, all have a -1 oxidation number and a 1- charge. So that the charge and the oxidation number match. But be careful, always, as I've mentioned before, with oxidation number, you put the charge then the number, oxidation number -1, but for indicating the charge on an atom, you would say then the other way around. So chloride ion 1- number followed by charge. Good. So we've got a few of the rules for oxidation numbers that you will be learning and seeing how they fall out from the rules. The rules come out from the definition of oxidation numbers. So what other rules are there? Well, there are a number of other rules. One of the other rules would be, say for example, oxygen normally has an oxidation number of -2. Well, what's going on there? Well, again, two things. Well, let's consider it ionically first. When oxygen bonds ionically, it's going to pick up 2 electrons, generally from, say, a group 1 metal, group 2 metal, transition metal. It's going to gain 2 electrons, and therefore it's going to have an oxidation number of -2. Covalently, oxygen is almost always going to be bonding covalently to something less electronegative than itself. So, when it bonds to that less electronegative atom, such as hydrogen or carbon, it is going to partially gain 2 electrons. Because it's more electronegative, it's going to bring those electrons towards itself. It's going to be, the electrons in the bond are going to be closer to the oxygen is going to partially gain electrons. So I think you can see now, if you think about it, that oxygen is going to have a different oxidation number if it's bonded to something more electronegative than itself. There is only one thing that's more electronegative than oxygen, that's fluorine. So in the case of when oxygen bonds with fluorine, which is not going to be a very normal situation, it's certainly not a compound. Oxygen bonded to fluorine, that's not going to be a bond you're going to encounter in any normal A-level compound. But if it were to bond to fluorine, oxygen's oxidation number would not be -2. Because the fluorine is more electronegative, it will partially gain the electrons, and so the oxidation number of the oxygen will be positive. And of course oxygen has the element O2, 2 oxygens bonding to each other, each oxygen sharing the electrons equally, oxidation number 0 again. Good, so I hope you're feeling a little bit more confident with how the definitions of oxidation numbers naturally lead into the rules that you would learn about oxidation numbers. There's a kind of list of a number of them. You probably read them in your textbook, and you may well have them in your A-level notes. But I hope that you can see clearly the link between the definition about an oxidation number and the rules. So let's apply it in a slightly more tricky scenario. Let's take potassium nitrate, KNO3. Assigning oxidation numbers to potassium nitrate, KNO3. How do you do it? Well, first of all, oxygen generally has an oxidation number of -2. And the oxygens in this case are going to be bonded to nitrogen. And so, oxygen being more electronegative than nitrogen, there is no reason why it shouldn't have its normal oxidation number. So it's going to partially gain 2 electrons as a result of bonding to the nitrogen, and therefore you can be confident that oxygen's oxidation number will be -2 as usual. What about the potassium? Well, from the rules we know that potassium, we know from bonding, from GCSE level knowledge, that potassium gives away its electron, gives away its electron when it bonds ionically, always ionically, being a group 1 metal, and so it's always going to have an oxidation number of +1. So now we've got the potassium at +1, we've got each of the 3 oxygens at -2, and the number of electrons lost and gained in a compound transferred between them has got to add up to 0. It's not ionically charged overall, so potassium nitrate, KNO3, has no overall charge, so the nitrogen's oxidation number must reflect this. The sum of the oxidation numbers must come to 0, because it's a neutral compound. So we have +1 for the potassium, we have -2 and -2 and -2 for the 3 oxygens. That comes to a total of -5, which means the nitrogen must be +5. And actually the name of potassium nitrate, KNO3, its systematic name is potassium nitrate 5, indicating with the 5 in the name, potassium nitrate 5, that it is in fact oxidation number +5 on the nitrogen. Well, I hope that simple example has helped. I hope that this video and the previous one have helped you feel a little bit more confident about the basics of redox chemistry. And now in the coming lessons we'll start to look at applying that in order to take a look at some equations to recognize whether they are redox or not redox, and for those that are redox to start to break them down into the oxidation part and the reduction part, which is to create the half equations. So I hope that's been helpful, and look forward to seeing you soon.